Algorithm design. If you have ever baked brownies, you know that you first have to gather the ingredients, then measure them, mix them together, prepare the pan, heat the oven, and cook them. If you forget the sugar, they don't taste good and you have to start over. If the oven is too hot, you may burn them. Determining the right steps, following them correctly and completely, and learning from mistakes are all part of the process of algorithm design. Algorithms are step-by-step instructions to get something done or the set of rules describing how something works. A recipe or a set of dance steps or the storyboard for an animation are all algorithms. Throughout the three previous steps in the computational thinking process, decomposition, pattern recognition, and abstraction, you have been working toward the design of an algorithm, or a set of instructions for completing a task. Algorithmic design moves the problem from the modeling phase to the operation stage. Algorithms take the form of a recipe or list of instructions that utilize efficiency and are written in such a way that they could allow for automation or use of computers to execute tasks, or they could simply be followed by a human. This set of instructions should be sequential, complete, accurate, and have a clear endpoint. If written for a computer, the algorithm must be comprised of a series of tasks written in a way that a computer is able to perform. In this video, we will first focus on algorithms that don't necessarily involve computers, and secondly on some of the key understandings necessary to prepare an algorithm so that it could be executed by a computer. Although the term algorithm might strike fear into the hearts of some who last encountered it in high school or college math classes, the definition of this term is simply a set of rules for solving a problem in a finite number of steps. An algorithm is a set of instructions and may or may not involve mathematics. For example, a simple, digestible algorithm that we all use is a recipe. The sequence of steps in a recipe must be followed in a certain order for the final product to taste good. You wouldn't bake brownies before you mix the ingredients together, or grease the pan after the batter has been poured in. Another simple example is getting dressed in the morning. If you put your jeans on before your underwear, you might draw some funny looks. We have been working with this necklace example problem throughout the course, one step at a time. A necklace is constructed from 20 blue beads and 14 red beads. Each blue bead costs 22 cents, while the red beads cost 33 cents each. The cost of the thread is 14 cents per inch, and 24 inches are required. What is the total cost of materials for the necklace? To create an algorithm, let's write down all the steps it takes to solve this problem. 1. Break the problem down into its components: blue beads, red beads, thread, their costs and amounts. 2. Identify subproblems that need to be solved. Determine the cost of each quantity of material, cost of blue beads, cost of red beads, cost of thread, and then add the costs of all three materials together. 3. Recognize patterns between subproblems. In this case, the first three subproblems can be solved in parallel. They don't have to be solved in a particular order. The second subproblem is sequential, meaning the costs for each material must be calculated before they are added together. 4. Set up an operation that can be used for the first subproblems: material quantity times material cost. 5. Calculate the cost for each type of material using the appropriate variables. And 6. Add the costs for each of the three materials together to determine the total cost of the necklace. Let's return to and review the Make a Monster example. We first decomposed the monsters into parts: eyes, nose, mouth, etc., and then found similarities between the features of the three monsters. We then used abstraction to replace the specific types of body parts with blanks so that any type of feature could be inserted. We have now created a recipe to use for our algorithm. We can use it to instruct other students to recreate the same or design new monsters based on the feature types. For example, if you provide this algorithm, you come up with this new monster. When we were discussing decomposition, we took some time to explore Bbot, the bee that moves a step at a time towards its destination. We looked at how its overall path was broken down into steps. Now we will focus on Beebot in terms of algorithms. Can you give Beebot the correct set of instructions to move from the start to the flower for level 3? How about level 5? Similar to Beebot, write out a set of instructions and have someone else follow your instructions exactly to complete a task. You can emulate Beebot by finding a tiled floor or using chalk on pavement to draw a grid. Take turns writing out instructions for each other to follow to move from square A to square B. Students must enact instructions exactly as they are written to see if all steps are correct. The person who wrote the instructions may need to revise them if they don't work. Here is another similar activity, but in this one the instructions are for building a structure rather than moving around. Students work in groups to develop algorithms to recreate models made from plastic bricks. Algorithmic design is critical in the computational thinking process. If a computer is not involved, algorithmic design provides a recipe or instructions to solve the problem. If a computer is involved, a human has to be able to tell it, in a language it can understand, how to solve the problem. For a computer to be able to aid in the efficiency of solving your problem, the algorithm must be comprised of a series of tasks written in a way that a computer is able to understand and perform. This involves a translation between the language of humans and the high-level language of computers. Humans speak languages like English, Spanish, or Arabic. Computers speak in bits, the basic unit of information in computing. You may have heard of the binary system, where the numbers 0 and 1 are used to communicate information. These are bits. Without getting too deep into computer science, suffice it to say that computers speak many different kinds of high-level languages, such as HTML or JavaScript, which are comprised of bits. Computer programmers work to create instructions through coding that are born from human ideas but translated for a computer to understand. WYSIWYG, what you see is what you get, interfaces can help you understand this concept. These are designed so that non-computer science savvy people can use computers to build what they need in their human language, but see how it translates into computer code. Here are a few necessary understandings when thinking about designing algorithms for computing or otherwise. For example, when baking, it is more clear to say, bake until a toothpick comes out clean, rather than just bake until done. An example for a computer could be, choose a number between 1,000 and 2,000, instead of just choose a large number. You need defined inputs and outputs. The input for the Make a Monster example is one name for each feature. The output of the algorithm is a new monster's face. For Beebot, it is a series of directional steps using forward, backward, left turn, and right turn. The output is the motion performed by the Beebot. You need to have a defined endpoint. Your algorithm should answer a question or produce a result and be clear when it has finished. You need to be able to interpret the computer's results. It is important that instructions are sequenced in the correct order to complete the task at hand. Flowcharts can help identify actions and the order in which they need to occur. You may find you have sets or pieces of the instructions that need to happen over and over again. This is called a loop or iteration. You may have conditional statements that affect the variables, if then, yes, no, true, false. In these cases, the first condition dictates the second. When designing an algorithm, it may be difficult to know if it is working and the outputs are correct. Different algorithms are developed to solve the same problems, and they can produce different results. This is why testing and revising algorithms is important. You can't depend on the computer or machine to do all the work. You have to interpret the results you get, think critically, and determine whether or not they make sense. You have now experienced all the steps involved in computational thinking. You have decomposed problems, identified patterns, abstracted information, and designed algorithms or instructions to solve a problem using a computer or not. But how do you know when the process is finished? How do you know when you are done? It can be difficult to know if you have accounted for all of the important factors and if you are truly solving the problem. Steps and skills involved in computational thinking can and should be iterated or repeated. Testing is the way to determine if it works or needs refinement. More often than not, a model that arises through computational thinking that is put into operation through algorithmic design must be reevaluated and refined through testing. If your solution doesn't quite work or make sense, you have to return to the earlier steps in the process and try to identify where a mistake may have occurred. This process of testing and identifying and learning from mistakes is the key to solving big problems. Just because you haven't learned how to write computer code doesn't mean you can't try creating algorithms for computers and programming. Several free online platforms allow you and your students to manipulate pre-written blocks of code that represent different tasks or actions. By sequencing, grouping, copying, repeating code disguised as colorful blocks, you are capable of creating and playing your own unique computer animations and games. So, you don't have to know how to program, write code, but you do have to understand algorithms, creating a logical set of instructions. In fact, doing this is a fun way to introduce algorithms to your students. Creating a game or animation in this way is an excellent method for learning how algorithms work. We'll use Scratch as an example of one of these programs. You can play with Scratch without creating an account via the Create tab, or if you set up a free account on the Scratch website, you will be able to save your projects. You are immediately able to start to experiment with creating algorithms. You can choose a sprite, character, and create and/or control its motion, looks, sounds, and other variables by dragging and stacking coded boxes. Concepts such as loops or iteration can be explored using the boxes in the Control section. You can access operators to create conditional clauses within your algorithms in both the Control and Operators sections. Operators are the conditional terms we talked about earlier. As you and your students' understanding advances, you can create and add in your own coded blocks for any functionality you can dream up. The ultimate goal for using computational power in solving problems is to solve seemingly unsolvable problems and to solve them as efficiently as possible. Figuring out what instructions to give a computer for it to solve a problem efficiently means thinking creatively. Computational thinking has led to many of the incredible tools that have become indispensable in our everyday lives. Without computational thinking, today's cars wouldn't run, and today's planes wouldn't fly as they are controlled by computers. Computational thinking has and continues to streamline and optimize efficiency in manufacturing processes to provide you with the products you buy. Computational thinking has led to such useful inventions as Google Maps and virtual reality. We as humans can learn from our mistakes and advance our understanding and knowledge to solve bigger and more difficult problems. We can work together, and it helps to have a systematic method like the steps of computational thinking to help us tackle seemingly impossible problems. Now especially, when solving problems can be greatly advanced by taking advantage of the efficiency of machines and computers, it is increasingly important to plan our problem-solving methods to address their incorporation. Today's students are tomorrow's problem solvers. Thank you for participating in this online professional development course.